Okay, guys. So today I'm just going to wrap up Unit 5 by doing another example of calculating the pH of a solution of a or of an analyte solution as you're titrating it. So last time I made a video. So this is Visible Learning Objective 5-4, acid-base titration. So um, last time I made a video, we did a weak acid. We had a weak acid in our titration flask, and we were slowly adding strong base to it. And so as we added the strong base to the weak acid in the flask, we wanted to be able to calculate the pH of the solution in the flask as we added the strong base, right? So obviously, we had a weak acid in the flask, so the pH of the solution initially was low, and as we had the strong base, it went high, right? So we're going to flip that, and we're going to do an example problem of we have a weak base in the flask to start with, and we're going to add strong acid to it, okay? So it's essentially the same steps, but you have to think about it a little bit more. You have to be a little bit more aware of what's going on because, again, when you're looking at the curve, the titration curve, the graph, pH versus the milliliters of strong acid in this case that we're adding, because it's the pH scale, and normally titration curves are going to be on the pH scale, not the pOH scale. When we talk about the half equivalence point where pH equals pKa, that's going to be the pKa, the negative log of the Ka of the conjugate acid of the base we're titrating. Okay, so hopefully that makes sense to you in words, but I'm going to show you an example of it. And so after that, that kind of wraps up Unit 5. We're going to have our tests soon, and you should be in good shape. 2 more units to go. All right, so let's get into it. So again, we did this example, or are going to do this example in class. And so I'm going to do a different one. But here's the scenario. So we're given ammonia, which is a weak base. We know the initial volume of the solution and the molarity of the ammonia. And we're titrating it with HCl, and we're given the molarity of the HCl. So what we have to recognize is we have a weak base, ammonia in this case, is being titrated by a strong acid, HCl. We're given the Kb for ammonia, and remember, that means we're also given the Ka for ammonium, its conjugate acid. And we want to calculate the pH after, this many milliliters of HCl have been added to our analyte flask, okay? So 0 all the way to 40 milliliters, all right? So that's the kind of scenario I'm talking about, all right? So I'm just going to go to a generic weak base strong acid titration. So let's say we have a weak base. I'm not going to even identify what the base is. I'm just going to say it's a base and it's weak, all right? I think I'm going to identify it in this problem as WB, weak base, okay? So a weak base is titrated by HCl. We have to recognize HCl is a strong acid. So here's the scenario, okay? 15 milliliters of a 0.5 molar solution of a weak base, we'll call it WB, okay, is titrated by a 0.375 molar solution of HCl, a strong acid. We're given the Kb of the base, 3.9 times 10 to the negative 6, and we want to calculate what the pH is going to be in the analyte flask, so in the flask, after the following volumes of HCl, of that HCl solution described right there, is added. And those volumes are 0 milliliters, 5 milliliters, 10 milliliters, 15 milliliters, 20 milliliters, and 25 milliliters, right? So that's our scenario. A weak base being titrated by strong acid, okay? So just kind of visualize what we should find. Let me make this a little bit smaller. Our titration curve should look something like this, right? We have pH, milliliters of our titrant, which is HCl in this case. And because we start out initially with weak base in the flask, we should have a high pH. And then as we add the HCl, remember we're going to get that initial jump towards the pKa, then we're going to get our buffer region, and then we'll get our S curve, and the equivalence point is the point of inflection. And what we should know about this scenario, especially after we've done the titration dry lab, is that this point, the equivalence point, where milliliters of HCl or moles of HCl equal moles of weak base, the pH should be below 7, because we have a weak base, strong acid scenario. The pH is going to be below 7 at the equivalence point. Okay, so start out high and go low. Equivalence point below a pH of 7. All right. So I'm going to call this weak base WB, and so that means its conjugate acid is HWB plus, right? So how do you get a conjugate acid of a weak base? You just add an H plus to it. So if this is the weak base, then this is its conjugate acid. So let's understand, as we start out with WB in our flask and we add H plus, this is the reaction that's going on, and it goes to completion, right? So the H plus from the HCl, we don't care about the chloride, will react with the weak base and form HWB plus. Or if you wanted to show, instead of H plus, if you wanted to show it as hydronium, then the hydronium reacts with the weak base to get HWB plus and water. Okay, so that's the reaction that's going on. And remember, a strong acid will react to completion with any base, whether it be weak or strong. So this reaction, that's why I didn't draw a double arrow. We're just saying that reaction goes to completion. Okay? All right, so that's the reaction that's going to completion. Some quick calculations to do to kind of help us map out this problem is, first let's find the equivalence point. So I want to know what volume of acid, of HCl, is going to be required to reach the equivalent point. And that's when we'll do MAVA equals MBVB. So here's our molarity of acid, our molarity of base, and our initial volume of the base, 15 milliliters and 0.5 moles per liter. And so that means 20 milliliters of HCl added is going to be our equivalence point. So real quick, half of that would be the half equivalence point. Okay, so we did MAVA equals MBVB to figure out the volume of acid needed to reach the equivalence point. And if we divide that by 2, that's the volume of acid needed to reach the half equivalence point. Okay. Other numbers I'm going to need for all the calculations I'm going to do here. Initial moles of weak base, so liters times molarity. So we started out, remember, with 15 milliliters of the weak base, right? If we go back up, we started out with 15 milliliters of our weak base, and that was the molarity. So if we do liters, 0.015 liters times molarity, that'll give us our initial moles of weak base. Let's understand that at the equivalence point, moles of H plus and moles of WB are equal. They take each other out. And so all the WB is going to be converted to HWB plus, its conjugate acid. So at the equivalence point, I know that's how many moles of HWB plus I have. Okay. Another thing I'm going to want to calculate is the Ka of the conjugate pair. So I was given the Kb, so if I go Kw divided by the Kb, remember the Kb was 3.9 times 10 to the negative 6. So if I do Kw, 1 times 10 to the negative 14, and I divide it by Kb, that'll give me the Ka of the conjugate pair, which is, in our case, is HWB plus. All right. So that's the Ka, and the negative log of that, the pKa, is 8.59. So just real quick, I know at 10 milliliters of HCl added, that's the half equivalence point, I know that's the pH. pH equals pKa at the half equivalence point. So there we go. We already did one of our calculations. Okay. I'll go back and review that, but just in your head. So these are all kind of the numbers I'm going to need, okay, to go into my calculations. All right. So we'll, make sure we have the Ka, we have the pKa, we have the moles of WB before any titration is started, before we added any HCl, and that would be equal to the number of moles of its conjugate acid at the equivalence point. Okay. So now we can kind of map it out a little bit better. We still know that the pH at the equivalence point is going to be below 7, but we know that that's going to be 20 milliliters, right? So now we know that volume, and we know half of that is going to be our midway of the buffer region, right? And that should have a pH of 8.59, which is the pKa of HWB plus, our conjugate acid. Okay. All right, so if we map it out, remember these are the milliliters we want to calculate the pH in our flask. So before the titration, before we add any HCl, it's just a weak base shortcut, okay? We know anytime between the start, so after 0.00 milliliters are added, but before the equivalence point, we're in the buffer zone. So we know 5 milliliters we're in the buffer zone, 10 milliliters we're in the buffer zone, 15 milliliters we're in the buffer zone. So we use the Henderson-Hasselbalch equation for 5 milliliters, 10 milliliters, and 15 milliliters of HCl added. Okay, but we can shortcut this one because that is our half equivalence point, and we know the pH is going to be equal to the pKa. But again, that comes from the Henderson-Hasselbalch, all right? So Henderson-Hasselbalch equation to figure this out, Henderson-Hasselbalch equation to figure this out. The equivalence point, we turn it into a weak acid shortcut because the only thing in our flask at the equivalence point, again, let's go back to the reaction. It's taking place, right? This reaction is going to completion. So at the equivalence point, moles of HB and moles of hydronium are equal to each other. So once they take each other out, the only thing that's left at the equivalence point is HWB plus. Now, the other stuff in the flask, I have water, but that's neutral. And I also have chloride, but that's neutral. So really, what's in my flask that will change the pH away from 7 is I have a weak acid in my flask. So if that's all I have in my flask that's going to change the pH from neutral, then it's just a weak acid shortcut, okay? So we know that's going to be our weak acid shortcut. And again, if we start a titration before the titration is a weak base shortcut, at the equivalence point, it's a weak acid shortcut. And if you remember the last video, we did the opposite. We started our titration, it was a weak acid shortcut, and then at the equivalence point, it turned into a weak base shortcut for the conjugate base. So this, we start out our titration with a weak base shortcut, and then at the equivalence point, it's the weak acid shortcut, which is, and the acid we're talking about is the conjugate acid of the weak base that we're titrating, okay? And then that means 25 milliliters of HCl added is beyond the equivalence point. So we reach the equivalence point at 20 milliliters of our HCl solution added. So anything beyond that is we've added excess H plus. There's no more WB in our solution beyond this point to take out any H plus. So all we have to do here is figure out what is the molarity of H plus in our solution. And if we take the negative log of that, that'll be our pH, okay? We don't have to worry about a weak acid or anything like that. We just need to figure out what the molarity is of H plus, okay? So let's go through the calculations. All right, so again, no HCl added, we just have a weak base shortcut. So I'm gonna say Kb equals x squared over 0.5. That was the molarity of our weak base. That was the Kb of our weak base. I'm gonna solve for x. Now remember, when you solve for x in a weak base shortcut, x is the OH minus concentration, okay? So 0.0014 moles per liter is our OH minus concentration. We take the negative log of that, but then we also subtract from 14 to get our pH. So the pH before we started the titration with our weak base in solution is 11.15. Okay, so 5 milliliters, remember we're in the buffer zone. I suggest you make a BCA chart, but in this case, we don't start out for the buffer. Initially, before we add any HCl, all we have is HB, and we don't have any HWB, or not HB, sorry, WB. All we have is WB, but we don't have any HWB plus. And remember, moles, so that's why I calculated that initial moles of WB. So we have 0.0075 moles before we add any HCl in our flask, and we have 0 HWBs, okay? The change is the amount of HCl we add. So we have to do liters of HCl, 0.005 times the molarity, which was 0.375. So that's how many moles of HB I'm gonna lose, and that's how many moles of HWB plus I'm gonna gain. So we subtract, we add, we get our new amounts. Now remember, if we wanted our new molarities here, we would divide by the new volume, which in our case, we started with 15 milliliters of weak base in the flask, and we added 5 milliliters. So our new volume is 20 milliliters right now. But we don't have to worry about that. We can just plug these into the Henderson-Hasselbalch. Now remember the way the Henderson-Hasselbalch works, right? This is the base component of my buffer, and this is the acid component. So remember, if you're doing pH equals pKa, it's base over acid. So it should be the WB amount on top and the HWB plus amount on the bottom here. And remember, we already calculated our pKa, so we'll say pH equals the pKa plus the log of that ratio, right? And we get 9.07, right? And it should make sense that we're above the pKa because we have more of the base component of our buffer than the acid, okay? Half equivalence point, right? We have equal amounts, so it would be pH equals pKa plus the log of 1, and the log of 1 is 0, so pH equals pKa, so we know pH equals 8.59. So 15 milliliters of HCl added. Again, I'm going to make my BCA. It's going to start out the same way. Before we started the titration, 0.0075 moles of WB and 0 moles of HWB plus. Again, the change is the amount of HCl I've added. And at this point, it would be 0.015 liters times the molarity of HCl. So 0.015 times 0.375, that's where we're getting these numbers. So I'm going to lose that much of my HB, or sorry, I keep saying HB, of my WB, and I'm going to get, I'm going to gain that many moles of HWB plus. I do my math. So after, I'm going to have this much amount of WB and this much amount of HWB plus, plug it into the Henderson-Hasselbalch. And now notice my pH is lower than the pKa because I have more of the acid component than the base component, okay, of my buffer system. All right, and remember, we can only use the Henderson-Hasselbalch if we have a buffer system, and we have a buffer system because we haven't reached the equivalence point yet, okay? So keep going. So now remember, this is the equivalence point. So what do we have in our flask? We don't have any H plus because it's all gone because it reacted with all the WB. And we don't have any WB because it's all gone because it reacted with the H plus. And those amounts are equal because we are at the equivalence point. That's what it means. So we have chloride, which is neutral, so we don't have to worry about it. We have water, which is neutral, so we don't have to worry about it. But what do we have? We have HWB plus, which is a weak acid. And we know it's a weak acid because it's the conjugate of a weak base, and the conjugate of a weak is weak. So it's a Ka shortcut, but the problem is we need to figure out the molarity of HWB plus at this point. Remember, we started with 15 milliliters of volume in our flask, and at this point we've added 20 milliliters of HCl. So our new volume is 35 milliliters. So I got to take my moles of HWB plus at the equivalence point. And remember, that's going to be equal to moles of WB that you started with. That's why I calculated that number at the beginning. So you calculate that number of weak base at the beginning, the number of moles, 0.0075 moles. And what we're going to be doing is dividing it by the new volume at the equivalence point, which is 35 milliliters. But for molarity, you got to divide by liters, 0.035 liters. So we get our molarity. So we have a molarity of our weak acid in solution. We're going to plug that in there. We can solve for the Ka. Remember, it's just, we've already solved for the Ka, but it's Kw divided by Kb. And now we're going to solve for X. And remember, in this shortcut, X is the H plus concentration. So once you get X, the negative log of that will be the pH. All right? So we'll plug in our numbers, solve for X. Remember, X in this shortcut, if it's a Ka shortcut, hydronium concentration, or H plus. Negative log of that gives us our pH. So there we go. Right? And remember, we were expecting it to be below 7 because it was a weak base, strong acid combo, and the pH at the equivalence point should always be below 7 if that's your combo. All right? All right. So the last one is beyond the equivalence point, where we've added 5 milliliters of HCl too much, right? So that means we have excess H plus. So the H plus was being taken out by the WB, but eventually we ran out of WB. And so now we add H plus, but there's no place for the H plus to go, right? It just has to remain in solution. So what we have to do is figure out how many moles of H plus are left. So remember, it's not all the moles of HCl that we've added, because a lot of that H plus has been taken out by WB. So the moles of H plus added to this point would be 0.025 liters times the molarity of HCl, which was 0.375. So that's how many moles of H plus I added. But this is the amount of moles of H plus I lose. Remember, that's equal to the moles of WB that I started with. All the WB takes out H plus in a 1-to-1 ratio. So if I do this minus that, that'll give me moles of H plus that remain, but I want molarity. So what do I have to do? I have to divide by the volume. Now, the new volume at this point of the titration, remember we started with 15 milliliters of our weak base in solution, and we added 25 milliliters of the acid. So our new volume is 40 milliliters, or 0.04 liters. So we'll take our moles of H plus that are still in the flask, because there was nothing for it to react with. We'll divide by the 0.04 liters. That'll give us our molarity. We'll take the negative log of that, and that'll be our pH, 1.33. Okay? So kind of our answers real quick. So remember, the whole goal was to figure out these pH values for milliliters of HCl added. Okay, so remember, this was the equivalence point. We figured that out by doing MAVA equals MBVB. Here's the pH at the equivalence point. Remember, it's got to be below 7, right? The half equivalence point is this divided by 2, and so we know pH equals pKa. Henderson-Hasselbalch in the buffer, Henderson-Hasselbalch with the buffer region. At the start, all we had was weak base, so we did a weak base shortcut here. Okay, weak acid shortcut here, and excess H plus here. Now, if we wanted to see what our titration curve would look like a little bit more accurately, now that we have it, we can plot these points. Okay, and notice my beautiful freehand graph that I made. You can tell that the space between each thing is equal. And I'm joking, of course. But, you know, we'd start up here way at, you know, the start is what, 11.15, so we're right above 11 here. That midpoint of the buffer region is 8.59. And I didn't add it, but like if you look at that, you know, this is the half equivalence point, 10 milliliters, right? This is the equivalence point, 20 milliliters. Beyond the equivalence point, 25 milliliters. And notice we get that initial jump towards the pKa, because remember, a buffer solution hangs out close to the pKa. So that's why you always get that kind of initial jump, and then we get our buffer region, and then we get our kind of S-curve. Our point of inflection is going to be at 20 milliliters and 4.62 pH. And so that's what our pH curve looks like. All right. All right. So hopefully that helps out. You know, if you understand this one in the previous video, you should be in really good shape to do the 5-4 assessment and, you know, take on the test. All right. So the test is going to be next week, and you have a practice test, you got a checklist. There's really no excuse for this one. You should really do a good job on the test. The only excuse is that you're behind in the class. All right, so don't let that be an excuse. Figure it out. All right, you got a week. All right.